All right, so now we're going to discuss maps between vector spaces. And the motivation for doing this, of course, is that because we're using modulo 2 arithmetic, the induced maps on homology are really just linear transformations between vector spaces. Okay, so we'd like to better understand it's like a bit more about these. So maps between vector spaces, and this is motivated by the fact that since we have sort of Z2 coefficients, right, the maps between homology are just linear maps between vector spaces. Okay, so let's see with a map F from U to V. Okay, and this is a linear map between vector spaces. Then we're going to define it's like the usual things. It's like which are the kernel, the image, and the co-kernel as follows. So the kernel, right, denoted KER of the map F, right, is just defined to be the set of points U in the vector space U such that F maps U to 0. Okay, in V, right, which is sort of understood, but let me just write that. Okay, and then there's the image, which is just IM of F, right? This is the set of V, it's like in V, such that there exists some U in U with the property that F of U is equal to V. Okay, and then the co-kernel, denoted COK of F is equal to V quotiented by the image of F. Okay. So, all right, so how do we realize this? It's like if F is represented by matrix. So if F is represented by a matrix, right, we can do the reduction we've done before, right? We can reduce F to get the kernel sort of spanned by the 0 columns, the image is spanned by the non-zero columns, and the co-kernel is spanned by the 0 rows. So a little bit of explanation is probably in order here. All right, so when I say the 0 rows and the 0 columns, I'm talking about it in the reduced form. But if you recall, it's like when we were talking about the reduction of the boundary operator of the boundary matrix. So, it's like we also had these, it's like U and V matrices, it's like which were then encoding what the basis you had chosen. It's like for U and V to represent the boundary map. Okay, so essentially then you have to look at the corresponding entries. It's like in the U and V's, it's like to tell you then what the actual it's like basis it's like for these kernels, images and co-kernels are, right? So this is sort of a natural extension of what we had before. Okay. So, and the point basically is that if you know what the kernel, the image, and the co-kernel are, you have basically all the things you really need in the following sense. Okay. So a fundamental result of linear algebra is that U and V are sort of completely described by these spaces. Okay, and what do I mean by that? So, so in particular, U is isomorphic to the kernel of F, direct sum with the image of F, and then V is isomorphic to the image of F, direct sum the co-kernel of F. Okay. All right. So this is going to have an interpretation in terms of this reduced matrix representing F, right? So this will have an interpretation involving the reduced matrix sort of representing F. Okay. So let's now look at three spaces, U, V, and W. Okay, so let's say F and G. Okay. So we say this sequence is exact, right? So this sequence is exact. At V, okay, if the image of F, okay, is equal to the kernel of G. All right, so if, so one observation obviously is that if this was now a sequence of chain groups and the F's and G's were the corresponding boundary maps, then the condition that something being exact at this point is equivalent to saying that the corresponding homology group at that point is trivial, right? If the image of F is equal to the kernel of G, then its quotient is trivial, right? Okay, so this implies in particular that the composition, right, G composed of F, is just zero map. Okay, so again, so if these three spaces were chain groups, and F and G were boundary maps, then exactness means that the homology at V is trivial, okay, which is what I said before. All right. But the point is that this idea of exactness of sequences is somehow more general than just what we see. It's like in homology. Okay, so let me sort of give you simple examples of exactness and what that implies for certain spaces. So let's look at two short sequences, for example. All right. So let's say that we have 0 maps to U maps to V, and then with a map F here. Okay. Right. And we say that, let's just say that this sequence is exact at U. Right. What that means is that the image of this map is equal to the kernel of F. Right. So the image of the 0 map, if you will, right, is equal to the kernel of F, right? So that means the kernel of F is equal to 0. Okay, so this basically implies, right, that F is 1-to-1, right, otherwise known as injective. Okay, now let's just say that we have another one. Let's say V maps to W, and that's G, and then it maps to 0, right? And we say that the image of this is equal to the kernel of this, right? So the image of G is equal to the kernel of the second map, but everything gets mapped to 0, so this kernel of the second map is just W. So that means that G is onto, okay, or surjective. Okay, so these are some examples, if you will, of what happens, it's like in this case of exact sequences. Okay, so there's this notion of what is called a short exact sequence. So the short exact sequence right, is a sequence of length 5 but where sort of the first and last spaces are just a 0. Okay, so it actually just looks like this. Let me just erase that, right? But it's just U, V, W, F, and G, but then there are a bunch of zeros here. Okay. So as the discussion above tells you, F is injective, and G is surjective. Okay. And then what happens in addition is that the space in the middle, it's like can be written in some nice way. It's like involving the F's and G's. So, all right. So in this case, what happens is that V is going to be isomorphic to the direct sum of the two spaces. Okay. So if we already know U and W, right, we can compute. We have computed V as well. Okay. All right. So this is again just some general notions of maps between spaces. We talked a bit about the, it's like the image, the range. The image, the kernel, and the co-kernels. We said how you can write down these U and V spaces in terms of things which are isomorphic. It's like to the images, the kernel and the co-kernels. And then we introduced this notion of exactness of a sequence, and in particular this idea of a short exact sequence. And the reason for doing this is because there's going to be a natural sort of exact sequence. It's like involving basically the chain groups and the relative chain groups, and so on. Okay, and so we'll see that in a little bit. Okay, so let me just stop here for now.